Okay, we have a problem here with the analysis of variance, which means we're going to look at the difference between means for more than two groups. In this particular problem, we're going to look at the difference between means for three groups. So a student at the university randomly selects 6 assistant professors, 6 associate professors, and 6 full professors at the university. Then the student research articles produced over the last 3 years. Here's just a look at the main idea of analysis of variance. In this first example here, what we have is some data for 3 separate groups. You can see there are 3 groups. We have sample means of 10, 15, and 20 for the 3 groups. That's going to be the difference between the sample means, or our effect. Now we can look and see that there's not much variability within each group. And it's pretty clear if you look at this graph that there really is a difference between means. That group 3 has a higher mean than group 2, which also has a higher mean than group 1. Let's look at another example here. Again, we have 3 groups, 1, 2, and 3. And again, we have sample means of 10, 15, and 20. So we have the same effect in these two examples with sample means of 10, 15, and 20. But if you look at the data, or the spread of the data in the second example, there's a lot more random error in this. So in this case, even though you had the same difference between sample means, there's so much error that you really can't discern which group is higher than either of the other groups. There's just too much error. And so what we're going to do with the analysis of variance is we're going to take the size of those effects, the differences between the 10, 15, and 20, that's going to be our numerator, and we're going to divide that by the amount of error. And what we're going to do is take the average variance for each group. And you can see that's going to be relatively low in the first example, or the example on the left, and pretty high on the second example. So here's the data for assistant, associate, and full professors. Again, these are just the number of articles that each individual had produced in the last 3 years. So what we want to know from this is, do we have enough evidence? Do we have compelling evidence, enough evidence to conclude that there's at least one difference between population research productivity, that is, number of articles produced over the last 3 years, and the rank for a professor? If so, which specific pairs of population means differ from one another? So here's just an overview of how we're going to solve the problem. We're going to formulate hypotheses. Then we're going to look up a critical value. In this case, we're going to look up the critical value in an F table. Then we're going to compute the test statistic. If you're following along with us, this is the same procedure we've been using all along. Formulate hypotheses, look up a critical value, compute a test statistic. In this case, we're going to compute something called mean square treatment to estimate the differences between the sample means, between the X bar 1, X bar 2, and X bar 3. Then we're going to compute mean square error to estimate the variation within each group. That's what I was telling you a second ago. We're going to compute the variance for each of the 3 groups and then take an average of that to estimate error. Then we're going to get the ratio of effect, mean square treatment, to error. And if that's high, we're going to reject HO. If that's low, we're going to fail to reject HO. Of course, that's the next thing, is to compare the test statistic and the critical value, and then decide whether you're going to reject or fail to reject HO. And then if we reject HO, we're just going to conclude now that there's at least one difference between population means. We're going to use another test, in this case Tukey's honestly significant difference test, or HSD. to locate specific differences between population means. You can also use Bonferroni confidence intervals, which we can generate with a computer, to look at those comparisons. Okay, our hypotheses. The research hypothesis is that there is an impact, in this case of professor rank, or whatever our treatment is, on the population mean productivity level. One way to state that is that there's at least one difference between population means, and one of the following is true: mu A not equal to mu B, mu A not equal to mu C, and or mu B not equal to mu C. The null hypothesis is that all three population means are equal. That would be no effect. So for the critical value, we're going to start with the calculation of degrees of freedom. And in this case, we're actually going to have two degrees of freedoms that we have to contend with. The first is the degrees of freedom from the numerator. That's just going to be k minus 1, where k is the number of groups. In this case, we had 3 groups, 3 ranks. And we'll subtract 1, and that's going to give us 2 degrees of freedom in the numerator. And then in the denominator, it's going to be the total sample size. We had 3 groups of 6. That's 18 minus k. That's 3, and that's going to be 15 degrees of freedom in the denominator. Then what you'll have to do is get the F table. If you haven't printed, or if you don't have a copy of that now, please print one. Go along the top till you get to 2. That's the degrees of freedom for the numerator. And then go down the table until you get to the row where you have 15. And with alpha equal 0.05, you're going to find a critical value of 3.7. So we're going to reject HO if the Ftest is greater than 3.7. And the Ftest will always be a one-tailed upper test. So it's always going to be reject if the Ftest is greater than whatever the critical value is, in this case 3.7. Here are some check figures for the calculation of descriptive statistics for each of the 3 groups, and then for the grand mean, x bar bar. That's the mean of the sample means. Okay, the 3 sample means are 4, 8, and 3. The grand mean then is the sum of those 3 divided by 3, or 4 plus 8 plus 3, that's 15 divided by 3 is 5, the mean of the sample means. And then the variances are 2, 2, and 0.4. Make sure when you're doing the calculations on these that you don't take the square root. This is a variance. These are variances, not standard deviations. Make sure you divide by n minus 1 for each group. Next, compute the Ftest. To do that, we'll first start with computing the effect, the mean square treatment. Okay, let's just break this formula down a little bit. Look at the upper left-hand side of the formula, the left-hand side of the numerator. That NA is just the sample size for group A. There were 6 in that sample. Then the sample mean for group A, which was 4, minus the overall mean, which is 5, square that. So if you look down below that, you have in the middle 4 minus 5 squared, that's 1, times 6 is 6. Then you go through that for each of the 3 terms on the top. Sum all those, you're going to get 84. Divide by 2, and you'll get a mean square treatment of 42. That's the size of the effect. Then we'll compute the error. Take those 3 variances and just get the average of those. That comes out to be 1.47. Then we'll compute the Ftest. That's just the ratio of the effect, the mean square treatment, that was 42, divided by the mean square error, which is 1.47. That comes out to be 28.57. And that's greater than the critical value of 3.7. So we're going to reject HO. And we can conclude, be confident, that there's at least one difference between population means. Be careful on this. It doesn't tell us where the difference is. It just tells us that there's at least one difference between population means. Or Professor Rank affects research productivity. To get more specific than that, we're going to have to make comparisons using Tukey's HSD, or honestly significant difference test. I'll warn you, if you go look in other texts and so on, there are a variety of tests that you can use for this. We're going to use Tukey's HSD. And to do that, we'll first compute the honestly significant difference. That's going to equal Q times the square root of MSE over NG. Just looking at the stuff under the square root, got our mean square error, that's 1.47. And then the sample size for each group is 6. Now the 3.67 is going to come from a Q table. And if you look at that Q table, you'll notice that similar to the F table, you have degrees of freedom for both the numerator and the denominator. Well, the numerator, it's just going to be K, that's 3. And then for the denominator, it's the same as it was for the analysis of variance for the F. In other words, the total sample size, 18, minus the number of groups, 3. So that's going to be 15. So make sure you can use the Q table for 3 and 15 degrees of freedom to get 3.67. Then just do the math and you'll get a 1.82. What that means is any difference between sample means greater than 1.82 will mean that there's also a difference between the corresponding population means. For example, the difference between x bar A and x bar B, we'll just get the absolute value of that. 4 minus 8 is 4. And the reason I have an asterisk by that is that's greater than 1.82. That means we're going to conclude that not only is there a difference between sample means, but there is a difference between the corresponding population means. More specifically, since the mean for group B is greater than it is for A in the sample, we're going to conclude that mu B is greater than mu A. For the next one, the difference between the two sample means for A and C is 1. That's not greater than 1.82, so we can't conclude that there's a difference between the means, the population means, for A and C. They could be the same, like a fail to reject HO. Then for groups B and C, group B is 8 minus 3, that's 5. There is a difference, that's greater than 1.82, so we'll conclude that the population mean for group B is greater than the population mean for group C. Taken together, we'll conclude that the population mean for group B is higher than the population means for both groups A and C. Associates have higher productivity than both assistant and full professors. By contrast, there's no discernible difference. We don't have compelling evidence that there's a difference between assistant and full professors. So is this enough evidence to conclude there's at least one difference between population mean research productivity and the three groups of Professor Rank? And finally, if so, which specific pairs of population means differ from one another?